fermionic systems. Then I will discuss nuclear physics on a lattice where I'll discuss the foundation and the applications. And then I come to strongly correlated electronic systems in low dimensions. Again, I discuss the foundations and the application, and I give a general summary and outlook. So why are we interested in strongly correlated or strongly interacting fermionic systems? So they come in different sizes, shapes, and forms. So here you see on the femtometer scale, you have hadrons or nucleons, where it's a many-body problem of quarks and gluons. And also atomic nuclei come on the femtometer scale, which are composites of protons and neutrons, here shown as black and red spheres. And then if you go up in scale to the nanometer scale, there are lots of interesting low-dimensional materials like graphene sheets, ribbons, fullerenes, all these tubes. And so these strongly interacting fermionic systems are challenged in particle, nuclear condensed matter physics, as well as material science and quantum chemistry. And the point is that the Pauli principle combined with strong interaction or strong correlations makes such system difficult to compute and or calculate. And in this talk, I will propose to merge effective field theories and Monte Carlo simulations to get access to such systems. And so the first thing I will have to explain what are effective field theories and Monte Carlo simulations on two very simple slides. So introduction to effective field theory, resolution matters. So if you can say that dynamics at long distances does not depend on what goes on at short distances, or you can also say equivalently low energy interactions do not care about the details of the high energy interactions. Or more pictorial way, you don't have to understand nuclear physics. These nuclei make up this bridge to build a bridge. It's just the wrong scale. Now, these are, of course, general statements which are easy to understand. So how can we make this into a precise and quantitative framework, which is called effective field theory? There are essentially four necessary and sufficient ingredients to construct an effective field theory. So first, you need scale separation. So what is low and what is high? That depends on your system, but there has to be clear separation. Then you have to know what are the active degrees of freedom. So what are the building blocks at these scales which you are considering? Then you have to know what are the symmetries or broken symmetries which constrain your interactions of these degrees of freedoms. And then you need the power counting, which means you have to organize the expansion in low over high. If you have a small parameter as the low energy over the high energy scale. And let me just remind you, for quantum particles, we work usually in canonical units h bar equals equal 1. So momentum is 1 over lambda, where lambda is the wavelength. And so for a relativistic particle, ESP, and for non-relativistic one, ESP square over 2m. And so long wavelengths means low momentum. So with a long wavelength, you can also look at coarse structures. And if you then increase the wavelengths, you can look at finer and finer structures. And by the way, just aside here, in a modern view, all quantum field theories are effective field theories because nobody believes anymore that a field theory can work on all energy scales. Now let me get into Monte Carlo simulations. So here I just show you the basic steps. So we start with the partition function, given in terms of some Hamiltonians and inverse temperature. So then either you have to discretize space in some volume L cubed, or if you have in condensed matter, the lattice already there, which is given by the ions. Then you also discretize time in some way. You introduce usually auxiliary fields. I explain this in more detail later. Then you integrate out the Grassmann variables, which leads to the so-called Fermi determinant M of phi. And this is shown here. It's usually a sparse matrix. And some more steps. And this is, for example, for the Hubbard model. Then you get these integrals, which you can then stochastically turn into sums, and then the sums you can evaluate stochastically by Monte Carlo simulation. Now, this is all nice and it's well worked out, of course, over many decades. The problem is that as soon as you go to finite chemical potential or finite density or doping in condensed matter system, this determinant M is no longer positive definite. So this is the basic assumption that you deal with a probability distribution no longer holds and the method essentially fails. And this is known as the fermion sign problem, and this is also known to be an NP-hard problem, shown in this paper by Troyer and Wiese. So you cannot have a general solution for that, but you can tailor problem-dependent solution to mitigate the sign problem. And so I will discuss three methods here. So in nuclear physics, there's Wigner's SU4 symmetry. From a long time ago, I also discussed what is called wave function matching. It's a new method which we just published in Nature last year, which you can apply to many systems. And then there are these Lifshitz templates where you contour deform your integrals, which you can apply, for example, to low-dimensional materials or in lattice QCD. I think I don't have time to discuss this in detail here. There are certain methods around which you can use for your system under investigation. So these are my basic slides. So EFT and Monte Carlo simulation are the questions at this point. But if you have a question, ask in between, don't wait to the end, because then you might lose track. Okay, don't see questions now. Now let's come to nuclear physics on the lattice. So I discuss this in a moment. So we discretize spacetime nuclear matter or scattering. And for the beginner, we have Timo Lade and I've written a textbook which contains all the basics and is very detailed in the steps, but here will be not very detailed. So first you might ask, why is this guy interested in nuclear physics? Now there are three reasons I can give. So also conventional matter only makes 5% of the total energy budget of the universe. So the matter we are made of is made of atomic nuclei. So you want to understand how we are made of, you better understand atomic nuclei. Then you know that we have this very successful standard model of the strong electromagnetic and weak forces, which is a gauge theory with quarks, leptons, and force carriers, and of course the Higgs boson. But you know that strongly interacting particles don't come in terms of quarks, they come in terms of hadrons and nuclei. And this structure formation is not really understood. So in a way, nuclear physics is the last frontier of the standard model. Everything else is essentially well understood. And you can also, by working on the lattice, you can access the multiverse, which means you can understand how fine-tuned reactions are by changing parameters like the fine structure constant or the quark masses. This I'm not going to discuss here, but that's another interesting aspect. Because you know that many processes which generate, for example, carbon in stars, there's a famous Hoyle state, which is very fine-tuned compared to the threshold of beryllium-8 plus helium-4, and that you can study how this fine-tuning depends on the parameters in such a simulation. Now, the nucleus is also an interesting quantum laboratory because there's an interplay between the non-perturbative strong interaction, which essentially keeps the nucleons together, but this is of course balanced by the Coulomb force between the protons. So it's an intricate interplay between electromagnetic and strong interactions, and there are many interesting phenomena one has to understand. For example, the drip line, so how many protons or neutrons can we add to a nucleus before it becomes unstable? Then there's clustering phenomena, so some nuclei appear as alpha clusters, and this has to be understood. And then there are many reactions, for example, which make up relevant elements of life, like carbon-12 or oxygen-16 in stars. And of course, there's also a large amount of few and many body methods existing. So I will discuss in a moment why one should come up with a new method. And then there's another aspect of nuclear physics, which are macroscopic nuclear matter, namely neutron stars. Neutron stars are 10 to the 69 neutrons, which are bound together by the gravitational force. But then, of course, the Fermi repulsion essentially keeps this thing stable. And neutron stars have gained prominence in the multi-messenger area, so by neutron star mergers and gravitational waves. So now one again is more interested in the equation state of neutron stars. And one should be able to describe these neutron stars by the same method you use for atomic nuclei. And so, as I said, I will advocate a new quantum many-body approach where chiral effective field theory for nuclear forces is mixed with stochastic methods. And this allows to tackle nuclear structure and reactions. So this is essentially the slide on the theory. So it's a new method, it's called nuclear lattice effective field theory, NLEFT. It's a new method to tackle nuclear many-body problems. So you discretize your space. So your three directions are discretized in lengths LS, 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 so X, Y, Z, and then you have Euclidean time LT. And then you have this grid shown here in two dimensions. And on the sides, so where these crossings are of the lines, you put the protons and the neutron. And the interaction of them are given by what has been told to us by Weinberg in the early 1990s, pion exchanges and contact interactions and Coulomb interaction, which is reviewed in this Ref mod fus. Now, important thing is that there's some lattice spacing, which is a distance between these lattice points. And this cannot go to 0 because we do not want to resolve the inner structure of protons and neutrons, so we cannot make it much smaller than 1 Fermi because the size of a nucleon is 0.85 Fermi. We don't want to resolve this. And we also don't make it too coarse. So if you go beyond 2 Fermi, then we cannot really see the nuclear interaction anymore because the interaction is too weak. So A is between 1 and 2 Fermi, and that means we have a maximum momentum because the edge of the Brillouin zone in such a lattice is given by pi over A, and this amounts to an ultraviolet cutoff between 300 and 600 MeV. That's perfectly okay because we are dealing with effective field theory, and effective field theory is only working in a finite range of energies or momenta. Now here you see that these Wigner SU4 symmetries. So Wigner found out that in 1937 that the leading order, you can write down the nuclear interactions in a way that they are not depending on spin and isospin. And this SU4 symmetry, which he found essentially is very helpful here. So here you see simulation of the ground state and the first excited 0 plus state, so-called Hoyle state. These are tomographic pictures in the XY plane. So this is with an SU4 symmetric interaction where you have no sign problem. And this is with an SU4 non-symmetric interaction, which is maybe more precise, but you see these horrible sign problems, so the signal is much, much worse. So for even nuclei, which means even number of protons and even number of neutrons, you can use SU4 very nicely. But as soon as you add additional protons and neutrons, then the SU4 symmetry is destroyed, and we need another method to come to equally precise calculations as this one. So we still need another method. So this was published in Nature Communications some say a year ago, and this guy is now a professor at the Hang University. He was a postdoc at that time. Yeah, sure. You mean the lattice spacing or the lattice size, the L or A? No, no. Of course, it's not a limitation because you work with an effective theory. You must have some finite momentum range. But of course, then there are still artifacts because rotational symmetry is broken, blah, 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 and these things. But that you can always store analytically by methods. I don't talk about this here, but this is more serious. But these are all handled with. So for example, if you have no more rotational symmetry, then there's mixing between partial waves, which normally would not mix, but then you add operators which vanish as A goes to 0, but you tune the coefficient so that the mixing in these unphysical waves is gone. No, because then this is you do in lattice QC, but here we have an effective field theory, so we have a finite cutoff. We need a finite cutoff in this theory. Well, this depends on the system, but usually we have something between 10 and 15 Fermi. The typical nucleus is a few Fermi, so finite volume effects are very much suppressed. You will see this later on a particular. You have usually periodic boundary conditions. Sometimes you see something from the edges. I will discuss this later in a particular application. So this is what is called wave function matching. It's a new method which we developed for quantum many-body systems, which was published in Nature last year. So the point is that you have some directly computable or soft Hamiltonian like the SU4 symmetric Hamiltonian, and then you have a more complicated, say, a chiral Hamiltonian. And what you can do is, if such a soft Hamiltonian exists, you can bring by a unitary transformation, that's why it's written on the circle here, you can bring this complicated Hamiltonian very close to this soft or directly computable Hamiltonian, and then you non-perturbably use this, and you can calculate all the corrections in perturbation theory between H prime, H chi prime, and HS. And so that means, for example, if you have a wave function originally like this blue one here, of course, such a behavior introduces strong sine oscillation because of the repulsion. What you do, you add some radius r, you match the wave function, the blue wave function to the soft wave function, the red one, and then inside you use the red one, and of course this smooth behavior does suppress sine oscillations. So with such a method you can go even to high precision where you don't have unpaired protons or neutrons. And this is applicable in many fields. Whenever you have a wave function which has such behavior, you can do that. And then you calculate in the standard way, you calculate the transfer matrix. You start with some wave function for your A body system. It can be free nucleons or more sophisticated initial or final state. You evolve in Euclidean time with your Hamiltonian, and then you form this matrix element, and then you see that from the logarithmic derivative, you get the so-called transient energy. And if you wait long enough in Euclidean time, you filter out the ground state, but you can also get to excited states by preparing states with the same quantum numbers, and then this becomes a matrix, and you diagonalize this matrix. Then the lowest state, for example, in carbon-12 here would be the ground state, then the next one would be the Hoyle state, the next one would be the third 0+ state, and so on. And so, for example, for helium-4, such a simulation looks like this. You start with 2 protons, 2 neutrons. You evolve them in Euclidean time. The interaction with pion exchanges, contact interaction, and that's essentially what you have to compute in this partition function. And important in this method is that you can get all possible configurations here shown in the 2-dimensional lattice. So 4 independent nucleons, you can have doublets, you can have triplets, you can even have quartets, meaning 2 protons spin up and down, 2 neutrons spin up and down. That's allowed by the Pauli principle. So all possible configurations are sampled, which are relevant depends on your system. You can also use them to prepare initial and final states, sometimes to improve the convergence to the asymptotic state. And you can also see that clustering, this is like an alpha particle, emerges naturally in this approach. Like, for example, in the shell model, you cannot get such cluster states. You would need an infinite basis, which numerically is not possible. Yes, in 4 dimensions. I just cannot plot this in 4 dimensions, so it's just a 2-dimensional poor man's plot of this. And then the other auxiliary fields, which often called Hubbard-Swiatkowicz transformation, but it's really Gaussian completion. So Carl Friedrich Gauss has done this first. So this is Monte Carlo. You can use it, but it's slow and not very precise. N-dagger n squared. So nucleon field. So what you do, you couple density to a scale field, and then you can, by Gaussian, express this by an integral to half and the coupling of the scalar field to this density. And then the amazing thing is, if you have this picture you've seen before, like a helium-4, now with this essentially can be mapped onto 4 independent world lines where with insertions of the scalar fields, and you can have scalar fields with some isospin index. You can also have pions, which you can also express as auxiliary fields. And you can see that this, of course, now is optimally suited for parallel computing, because you can parallelly do these 4 world lines in the same shot if you have a good parallel computer. And so that is important because that allows you to really go to large systems. And now I see what you can achieve with this. So this is now calculation of nuclear binding energies to next to leading order in the expansion, which I don't discuss here in detail. You can ask me afterwards, published in this paper. So here you see the binding energies from the deuterium is not plotted, but it's also in the fit from helium-3 up to nickel-58. And you see yellow-colored things, they're used to fit because there's 3 nucleon forces which are smeared over the lattice. You need a certain number of nuclei to which you fit. These are the yellow ones, and then the red ones you predict. And you see that the prediction is quite good. For example, the ground state of carbon-12 is fitted, but then the first excited 2+ state comes out correctly, and then the famous Hoyle state comes also out correctly. You see here neon 20 up to nickel-58. This is the binding energy per nucleon in these states, comes out quite nicely. So it's an excellent starting point for precision studies. And now we can make predictions. So now we calculate the charge radii of these nuclei, and there's no more parameters, so we can all predict them all. All the parameters are fixed. And you see experiment is blue, and our prediction at N3 is red. And you see that except from helium-6, this is a very good agreement. This is a halo nucleus. It's not so surprising. We get very, very good agreement. Some have large error bars, but these are statistical uncertainties because we run out of computer time. That's not systematic. So they can be improved. And the nice thing is that we don't have the radius problem because other ab initio methods, which can calculate the masses equally well as ours, predict the radii to be factors of some 10% or 20% too low. And we don't have this problem in our approach. This is nice because it's a big problem in nuclear theory. Now then we can also look at matter, and here I come to the boundary conditions. So this is the equation of state of neutron matter. So the red points are, and compared to other calculations, in particular, it's similar to this famous Akmal-Pandri-Ravenhall semi-phenomenological, much used equation of state from the late 1990s, which are these black dots. And here is nuclear matter, and we see that with nuclear matter, we get the binding of -16 MeV per nucleon at nuclear matter saturation density. That's nuclear matter saturation density 10 to the -16 inverse Fermi cubed. And here you see boundary effects, which you wanted. This is an effect of the boundary, that is zigzag behavior. But this you can improve by so-called twisted boundary conditions where this disappears. Here we didn't have the computer time to do that. But when you enforce the so-called twisted boundary condition, you get a smooth curve instead of this up and down. And then we can look at the drip lines. So for example, these are calculations of the carbon-oxygen isotope up to the drip lines here. And you see we get a good agreement with experiments. So the ones which were fitted get shown in yellow, and in red are the predictions. So we can really if we add neutrons, more and more neutrons, we can really describe the behavior without any tuning any parameter anymore. So the 3-nucleon forces turn out to be rather important in these neutron-rich nuclei. And we also discovered some universal features of the neutron correlations here, which you can also see in other chains of isotopes. And this is particularly interesting. This was a recent calculation where we looked at beryllium isotopes in the P shell from 7 beryllium to 12 beryllium. And this is interesting because in this you have lots of interesting structures. You have these compact 2 helium-4, 2 alpha cluster states, but then you also have states where you have 1 or 2 halos, so single neutrons which are far out. And you can see that we can get this experimental spectrum. So all parameters are fixed to very good precision. The N3LO is the red one, and the black are the data. In particular, these lowest order, so the ground state in beryllium-11, this 1/2 plus state, this was a long problem for nuclear structure theory, which in our approach comes out very naturally. And so we have a new method to quantify these nuclear shapes, which these are just pictorials. They're not one in this paper you find details on that. But in this calculation, we get clusters, halos, and molecular orbitals in one shot. And this is the last thing I want to say. Nuclear physics, I told about nuclear matter and neutron stars. And so we did a calculation together with Huitong and Sarah Tizari, which is published and in preparation, of beta-stable matter with neutrons, protons, also lambda hyperons, because they appear at some density in neutron stars, electrons, and muons. And we use the so-called minimal model, so not the full N3LO calculation, but the minimal model which describes well nuclear matter, neutron matter, and also hypernuclei with 2 and 3 body forces. And so the equation of state was calculated really ab initio with up to 232 neutrons in a box of that volume, 288 Fermi cubed. And this is essentially 6 times nuclear matter density, and we had up to 24 protons and 34 lambda hyperons. And here you see the mass-radius relation which we get. So that's the radius of the neutron star in kilometers. That's the mass in terms of the solar masses. And we get this famous behavior that you can get up above two solar masses. And these are famous results from the NICER experiment, which are perfectly consistent with our calculation. And here we show the so-called tidal deformability of a neutron star, which you can get from gravitational wave signals. So with large uncertainties, but again, our calculation is perfectly consistent with these data. And in fact, it's the first ab initio calculation of neutron stars consistent with all these observational constraints. And also the binding energy of light hypernuclei are consistent with the data, which I didn't show here. So there are lambda present, but there's no lambda puzzle. So this is quite an achievement, because nobody was saying that this would be able, that you can put nuclear matter up to 6 times nuclear matter density in a finite volume. This we are presently investigating. there has been some Bayesian inference from data by the Munich group, and they claim that there's no phase transition. So they use all the data with some Bayesian model, but we are presently calculating this and want to see whether we also get the same result. So from Bayesian inference, it looks like there's no phase transition, but we will do a direct calculation. Yeah, it's neutrons, some protons, and also some lambda hyperons, because at around 3 times nuclear matter density, hyperons appear, because then the strangeness equation, chemical potential is the same as a non-strange equation state. So you get some hyperons. So you cannot really avoid them. But this is quite an achievement, and so we are presently calculating the possible phase transition in this to answer this also. But from Bayesian inference, it looks like there should be none just from the data. Okay, and that's, I think, I wanted to say on nuclear physics. So this nuclear lattice simulations is a new quantum many-body approach. We have already some highly visible results obtained, some papers in Nature and many papers in PRL. So recent development are these interactions with the so-called wave function matching, which allows you to go to high precision. So we have first promising results for nuclear structure, nuclear matter, and scattering, which I didn't show. We also have first results for beta decays in this paper, and ultimately, of course, we want to calculate neutrinoless double beta decay, because it tells us something about the nature of the neutrino, whether it's Dirac or Majorana, and also hypernuclei under investigation in this paper. So stay tuned for more results. Now I completely change gear and come to strongly correlated electronic systems in low dimensions, but you will see we can use the same kinds of methods to get some new insight into these. So it's more interesting for the condensed matter people. So why low-dimensional materials, like I showed already, these graphene sheets, tubes, ribbons, or fullerenes? So their quantum effect and strong correlations induce novel phenomena, often called emergent phenomena in the literature. So for example, you can use this for novel quantum electronics or fault-tolerant quantum computing. And here you see that you have some lattices, a bipartite lattice, where the electrons can have strong correlation or strong interaction. Now the scales of the order nanometer angstrom. And these can also be tackled by Monte Carlo simulations and effective field theories. Now, why are there strong correlations in low-d materials? That you can easily understand by comparing the Coulomb energy to the kinetic energy of an electron in a d-dimensional system. And you can derive this formula. There's this factor gamma, which is the quotient of the ratio of the Coulomb to the kinetic energy, and this essentially is N0, the fiducial density over the electron density. And the fiducial density, of course, involves the effective mass in the system you consider and the dielectric constant, and then this to the 1 over d. So you see that the strength of the electron correlation depends on the density of electrons and on the dimensionality of the system. So if this is smaller than 1, then you can use perturbation theory. But if this is larger than 1, you have to use non-perturbative methods. And in general, lower dimensions, because it's 1 over d, enhance correlations, and also the d here. So graphene in two-dimensional system is a good example. There's a linear dispersion for the electrons, and from that you can calculate this gamma between 2 to 3, up to 2 to 3. So the electrons in graphene are strongly interacting. And all the systems I consider now have strongly interacting electrons. Yeah, now I'm talking about QED, but I still have fermions, which are the electrons which are strongly interacting. And the lattice is given by the ions instead of my space-time lattice. So it's very different systems, but they share similarities, and you will see the results speak for themselves. So no, it's this. So now, okay, to make this crystal clear, now we have, sorry, wrong direction. Now we have electrons sitting on our lattice. Now the lattice is given by the ions instead of just as a calculation tool. But the fermions are now the electrons instead of the protons and neutrons, but they are still strongly interacting or strongly correlated. And I have again the lattice, so I can use the same methods, as you will see. This is a nice thing that you can use often methods for seemingly very different systems, but in a way they are very similar because they share the same basic assumption that there's an underlying lattice and strong correlations or interaction between the fermionic degrees of freedom. Okay, so important in low-D materials are particularly the symmetries as usual. So there's time reversal, which means E of k is E of minus k. So here's k, the momentum, and this is your energy. Then there's charge conjugation, or condensed matter people call this particle hole symmetry, c squared plus minus 1. This is E plus of k is minus E minus of minus k. And then often if you have sublattice symmetry, which we call chiral symmetry, E plus of k is minus E minus of k. So for example, in such a bipartite lattice, you can have this chiral or sublattice symmetry. Now you know that there's no spontaneous symmetry breaking in D less or equal than 2 dimensions, so no Goldstone modes. But of course, you know that the phases of matter are classified topologically, and all symmetry classes are cataloged. This is this famous 10-fold way of condensed matter physics compared to the 8-fold way of particle physics. But this is, of course, done for non-interacting systems. And for example, you can see this in this review of Zhu et al. Now I come to particular systems where topology emerges, and I want to discuss first hybrid nanoribbons. So we consider here the so-called armchair graphene nanoribbons, AGNRs. Because of their lookout, people call them armchair. I've never really understood this, but that's how they are called. And they are defined by the shape of the axis. And so you see here 7-9 ribbon. 7 means this is the width, and the length is given by how often this basic pattern repeats. There's 3 here and 5 here. So the 7, 1, 2, 3, 4, 5, 6, 7. And this is a 9 ribbon, where you have 9 in the basic cell parts. And so if you put 2 of them together, because they have different topologies, you can get these localized states. I show this in a moment here on the edges. These dots are the density of these edge states. And you can see here, this is from a Nature paper from already some years ago, where people have really fabricated such as 7, 9, AGNR. And the other thing, you also calculate these 13 other topology we looked at are these 13, 15 ribbons, which are a bit broader. So you can see it's 13 is again this unit cell. This is 13, and the unit cell here is 15. And there's localization. So here you see that for the 7-9 AGNR. So there's this topological invariance Z2, which is 0 here, and Z1. And then because of this different topology, you get these localized states on the edges. Here's these red dots and the blue dots. And these are essentially related to the fact that you have a 0 energy state. So that's the spectrum. So the Dirac is completely filled. And then there's a gap between the 0 energy state and the bulk states, which are these black lines. And this, in fact, can be seen experimentally. Here's a realization of such a gapless state on some nanowires, details in these publications. And of course, they have many potential applications in topological quantum dots, fault and quantum computing. But the theoretical analysis is based on non-analytic dynamics. I will come to this in a moment. Yes. No. The electron, some effective mass. Does this one here? Yeah. So here the gapless states are essentially energy 0. That's true. And so now, before I come to the interacting part, let me tell you that we found some new type of localization. So the standard law is if you connect gapped AGRs like the 7-9, you get this localization. Shown here is the density per unit cell. So this is 10 to the minus 2, this is 10 to the minus 3, 10 to the minus 4, in case you can't read this. And you see you have exactly the largest density here in the edges, where the red dots and the blue dots are. And the rest is of these wave function decay exponentially, that you have some overlap. That's why they go like this. Now this we call Fuji localization because it looks like Mount Fuji, and this is of course well known in the literature. But we also found you can connect a gap with a gapless AGNR, like a 9-11 hybrid, and then you see that you get really localization over a large part of the ribbon. So here you have gap. Here you have a bit of localization, then you have an area of localization, and then again, no localization, area of localization. And of course, we call it then Kilimanjaro localization because it looks like Mount Kilimanjaro. And this is something which is new and people have not explored yet, because it offers some new possibility, because you have the energy zero states not just on the edges of these HNRs, but you can spread them over your ribbon, and this maybe gives you some ways to new possibility to engineer and manufacture them. Now let me discuss the question, what happens if you switch on interaction? As I said, all this topological classification is built for the non-interacting system, so you can ask the question, what happens when I switch on interactions? A second, please. So for that, we use the quantum Monte Carlo simulations of this Hubbard model with an interaction. So this is our non-interacting theory, where you have some hopping parameter t, and then you have some interaction, some on-site interaction with some strength u. And you can see here, if you look at the picture, so u equal 1 all in units of t. So you always normalize this to this. This is your canonical energy in the system. So u equal 1 means 1 times t and so on. So u equal 1, 2, 3, and 4. And you see these pictures look essentially the same, which means the localization is still there if you switch on the interaction. But of course, the energy changes. Here you see the energy for various strengths of your interaction. So 1, 2, 3, and 4. Of course, the energy changes, but the localization persists. And this is for particular 7-9 geometry, but we also shown this for other geometry. So that's nice, because that means if you switch on even strong interaction like here, this localization is still there. And let me digress for a moment, because this in a way has origin in particle physics, because you know it's very different to represent chiral fermions on a lattice. There's this no-go theorem by Nielsen-Nimonier, and this was by David Kaplan by saying that you can put these fermions on a lattice in a fictitious fifth dimension. So you put the left-handed fermions on this side of the wall, and then the right-handed quarks on this side of the wall, and the four-dimensional physics essentially given here. And you see that they kind of overlap. There's a residual symmetry breaking, so you can do that. This has also been a lattice QCD. But you see that if you now look at this density behavior, it looks very much like the fiducial density in the hybrid nanoribbons. In fact, hybrid nanoribbons provide a physical manifestation of these domain Wolf fermions. That's a nice interplay between these fields. But let me now come back to the EFT. So for a moment, we have only done Monte Carlo simulations, but now we also want to do an EFT for nanoribbons. And we have all ingredients, separation of scales. You see here is our localized states with zero energy, and there's this difference to the bulk where all these other states sit, and this is delta E. So separation of states is given. The relevant degrees of freedom are, of course, the localized edge states. The interactions are constrained by the symmetries, T, C, and S. And we have a power counting if D is Q is some small momentum off the or impinging on the degrees of freedom, then we essentially expand in Q over delta E. And now let's see how this works. So I just do this directly for the interacting case. So you can diagonalize this Hamiltonian, which is shown here. So this is our standard Hamiltonian, which has two hopping parameters for the A sides and one for the B sides. This is a non-interacting case. So you can diagonalize, bring this in this form. Then you have these parameters TA and TB here. And these you can get from the non-interacting theory. I don't show this here, but this is shown in this paper. And then you can, the interaction can be described by what is called a staggered mass, MS, or should be M sub S, not MS here. M sub S, this is the energy gap symmetric around the Fermi energy, plus of course particle hole and chiral symmetry. Now here, what we do here, so now we have this effective theory, and we have simulations for various strengths from U equal 0 to 3 with some intermediate values. So the dots are the simulation, and then we can fit the effective theory, because there's of course some uncertainty. We can fit the effective theory to this data, and then you get this description here shown by these these various colored bands. And this is given for the circuitry. So a 7-9, so the length of the 7 bits nanorhythm is 3, and then we have ms length of the 9 bits nanorhythm. So ms is here given from 2 to 10. And now we use a different geometry. We have M7 with M7, which runs from 2 to 10, and 9, 8. And now we can predict the spectrum just using the same parameters. And this is shown again by these colored bands. And now these simulations have been done afterwards. So the dots are the simulation which have been done afterwards. And you see that the predicted spectrum is really complete agreement with a complete numerical solution. But of course, the effective field theory calculation is much, much simpler than the full simulation. So once you have fitted your parameters, you can use this effective field theory to predict the spectrum for many different other geometries. So that's very nice, and it shows how powerful these methods are if you combine them. And the final thing I want to discuss in the last 5 or so minutes is this SSH model, Schuschriefer-Heger, which is very famous in condensed matter physics. So it's a model where you have 2 different ions in one cell called A and B, and there's an intercell hopping parameter T1 and an intracell hopping parameter T2, and you usually have an even side. And then the localization or topology depends on the relative hopping parameters T1 and T2. And so there's topology if T1 is smaller T2. This can be shown. And you see the energy is roughly 0 because you have this, if the line is not very extended, this wave function decay exponentially, so there's still some finite overlap, which means the energy doesn't go exactly to 0. So if you make this very long, then of course the energy goes to 0. Now, however, if T1 is bigger T2, you have this trivial state, and then there's this gapless state if T1 is equal to T2. So that is well known. Now, what this I don't have to discuss in detail, that's well known. And you can see that you can manufacture this model by silicon quantum dot or artificial lattices shown in these papers. This is from this silicon quantum dot, and you see you have this topological state, which is this thing here for T1 smaller T2. So that in this paper, these are called V and W. And for the trivial state, you see there is no, for T1 larger T2, you have the trivial state, there's no topology. And the disadvantage, of course, is a sensitive parameter choice. You have to ensure that T1 is smaller T2. And of course, your chain has to be long enough to reduce the wave function overlap. Now, there is a different way to generate localization in the SSH model. And what you see now is very simple, but I'm very amazed that nobody has ever thought about this. Namely, you take an odd side. Now you add an additional, say A or B, doesn't matter. You add just one additional species on one end. And this will be put on the archive on Friday. It will appear next week. So it's with the postdoc Lin Wang and Tom Lu at Jülich. So now you find you have different types of localization for all values of the hopping parameters. So for T1, because there's chiral symmetry or sublattice symmetry, and then your localization depends on the right or on the left as you have an A or B type addition. So if you, like here, you have an A type addition, you get these T1 smaller T0, you get energy 0 in this case, so the localization on the left side. For T1 large, now bigger T2, you get localization on the right side, and if you put a B, it's just the other way around. And of course, you get an energy 0 state for T1 equal to T2. So this is nice because it's independent of parameter choice, and there's no length requirement. You see here that there's nothing on the other side because of the sublattice symmetry, which we had before. And I don't know, this, if somebody tells me this is known, please tell me, because we looked very hard, but this is not to be known. Also, it's there a happy space? Yes, that's the energy 0 state. And it appears for all combinations of T1 and T2. And now what you can do, you can add defects. So you introduce defects, which means you change the strengths between the coupling of the ions either in the AB or in the BA system. So like, for example, you have this energy 0 state with no defects looks like this, but now you can, for example, change this T2 to some defect by just adding some ion which has a different coupling, which you call D2, and then you see that you suddenly get different types of localizations. But to control them, you need interactions, and I'll show you how to do this. So you can add a Hubbard on-site interaction, or this is the old SSH model, and you add again this Hubbard term. So you will see that we generate spin singlet centers like this above some critical value of U. So for no interactions, you get this picture I just showed you. But now, if you add these defects and you have a large enough U, you can really generate such spin singlet centers. And if you increase U, then they get stronger localized. So this is, of course, a possible platform for magnetism, spintronics, quantum computation, and simulations. And more amazing, you can play very different games. You can now, for example, take here this spin centers where you have total spin 1/2 in the ground state, but you can find that there's a state with S equals 3/2 where you just flip one of these two, which is just slightly above the ground state, and then there are many of them, and then of course Z equals 5/2. Again, energy is not very much above the ground state, and you can couple these different spin configurations by an external magnetic field. For the even model, you can do the same things with SZ equals 0, 1, 2, and so on. And this allows you to engineer or manipulate spin qubits with different spins, which is nice, I think. But we have not thought about applications so far, so ideas are very welcome. Yes, the Hamiltonian, let me show you again. So there's this usual SSH Hamiltonian at the Hubbard on-site interaction, which you need for that. Otherwise, you cannot control what's going on with the centers. And you, of course, you can control by the type of ions. So you can make different by putting different ions as defects. Okay, so there's this amazing multitude of interesting spin states which you can manufacture and engineer. But this is so new that we have not even thought about this, but ideas are welcome. And now the last thing I want to discuss, you can do the same, play the same games in graphene nanosystems, because this is a graphene nanosystem, which is similar to the SSH model. There are two sides, A and B in one unit cell. So which means you have chiral or sublattice symmetry. And again, if you have a system with odd sides, it's similar to the SSH model with equal hoppings. And then on such a system, you can localize the states either on the right side or the left side, which is already nice. But even more, if you put defects, you can even control the localization to some upper or lower part of the ribbon. So that's something also very new, which we are presently writing up. So consequence application need to be investigated. If somebody has ideas, please let me know. So my intermediate summary on this is that low D materials are amenable to MC simulation effective field trees. So you can borrow methods from lattice field theory or nuclear physics field theory in QCD and strong interactions. And you can also allow calculated EFTs here for quicker access. I showed you this for the armchair graphene nanoribbons, where the EFT is quickly written down. We have also written down the EFT for the other systems here. I discussed later, but this is not yet worked out in detail, so I couldn't show you results. For recent developments here, you have localizations in these armchair graphene nanoribbons, and we found this new type of localization, Kilimanjaro, where you have a gap in the non-gap system connected. And we could also show by Monte Carlo simulation that localization persists in the presence of the strong interactions. Now then there's a new twist in this SSH model with an odd number of sites, because then the localization is there for all values of the hopping parameters. And you can essentially control this by adding in defects. And by adding in defects and interactions, you can essentially have spin centers with singlet, triplet, and so on, which you can move around your spin shape depending on the intercell hopping parameter and on the strength of your defect, which is given by different forms of ions. And you can do a similar engineering in graphene nanosystems. So there are much more to come. Stay tuned. And my final summary is this one. So strongly intact fermion system pose severe challenges. So they can be tackled with EFT and/or Monte Carlo or stochastic methods. And there has been large progress made in the last few years. We have new insights in nuclear structure, nuclear matter, and also scattering, which I didn't show here. But also now we get some new insight into topological matter and how to engineer it. And I think that more interaction between the fields is needed further because usually particle physics, nuclear physics people don't talk to condensed matter people and the other way around. But this, I think, is not beneficial to the field. And you can see methods which have in one, you can make large progress in the other field and the other way around. So that's all I wanted to say. I'm open for questions. Thank you for your attention.
Is there any question? Yeah. Thanks for your nice talk. Still, I didn't get the main message that how did you borrow from the nuclear physics and lattice simulation, the Monte Carlo way that you used, and which part that you borrowed to come to the QED part and for electrons actually? Because so that one is non-abelian, this one is abelian, and when you are using some techniques, there should be main differences. For example, for solving the sign problem at finite density.
Yeah, okay. So the method borrowed are, of course, the simulation. It doesn't matter whether you have abelian or non-abelian. But of course, the sign problem here is different. The sign problem comes in when you look at, like, for example, bipartite lattices where you dope one kind of like perilene. You see, in perilene, you have this problem.
Yeah, from this point of view, yes, but electron doesn't have any structure what proton have.
No, but proton in the simulation also had no structure because the protons were considered, that's why we didn't go with A below 1 Fermi, so not to see the structure of the protons. Of course, it has a finite radius, you can fold this in, but this is not relevant for the simulations. You're not doing lattice QCD where you solve this substructure in terms of quarks and gluons. So the methods are the same. The simulation, of course, simulation is different for non-abelian and abelian theory. That's true, but still, if you look at systems like perilene or so, where you have like bipartite systems where you dope only one part, then you can see that you again get the sign problem. So it also appears in these systems. And the EFTs I showed you that you can essentially, in the first thing you use the EFT to define your interaction on the lattice, but here you can also use the EFTs to make much simpler calculations once you have pinned down your parameters.
Okay, thank you.
So these topological phases, they usually, or in some cases, admit degenerate ground states. Can you see these degenerations also with these methods, or compute these ground states?
Yeah. I mean, the ground state, if the guy would. I mean, you've seen this here. This essentially is the ground state energy per cell, which is largest at this localization where this density is large and it drops off exponentially, but then the next ribbon comes and you get this behavior. So that's essentially the ground state wave function.
But one can also get the degeneration. I mean, how many ground states there are and so on.
Oh, this depends on the length of your ribbon, and this is all finite systems. So you get a finite number of these overlapping things. So you can see that in principle this goes also here, but since there's a next ribbon coming, then it's cut off. But this depends, of course, on the length, how many you put together. But of course, they are all degenerate. That's why you get this repeating picture.
Okay, thanks. Yeah.
What are these numbers? 7, 9, and
yeah, okay. Let me show you this. This was maybe too fast for people who are not in the game. Okay, here's 7. So you see unit cell is red dots here. You see 1, 2, 3, 4, 5, 6, 7. That's the unit part of this 7 ribbon. And then you have, in this case, you have 3 of them. So this is 9 because in the unit cell you have 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's the width. It's given by one of these unit cells. And then you patch a number of them, m, whatever, together. And here you see 13, 15. You see the unit cell is this thing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And the same here, you get 15 if you look at the unit cell. And then you can patch n number of them together for the length of your string.
Theoretically, this ribbon should be very, very long, or it doesn't matter?
Principle, so of course in nature it's not very long. But with theory, in principle, you usually deal with periodic boundary conditions, so that you say that, so you don't do the infinite thing, you just say that this end, if you have symmetric thing, this end reappears here. But of course, if you want to have a really zero energy state, then the ribbon should really go very long, because otherwise there's some overlap of.
Well, when you want to see these patterns, this Fuji or Kilimanjaro, then
this is independent of the length. So you can repeat this many times, but you can also repeat this many times. So it's just that the one has a gap and the other has no gap. And then this will always appear. And the length then depends on which kind of ribbons you put together. Some have smaller overlap and some have larger. But this pattern, if you make this infinite long, just repeats and repeats and repeats. Here it doesn't repeat because, of course, this is a finite length and here's the same. But if you have this standard localization, this will just keep on repeating.
It's always some kind of this.
Yeah, the Hamiltonian is there's some free part where you have some spin generated with standard annihilation creation operators. So it can be up and down, which have some strengths. And then you have some interaction, which is always this squared Hubbard-like interaction. You can do more complicated stuff, but this I'll discuss here. But this is the most simple model for these kind of systems. That's kind of the standard model of condensed matter two-dimensional systems. And of course, as I've shown, these things can be fabricated. So you can really get such things fabricated in the lab.
A question to the first part, partly because I was late, but so you got results about beryllium, about various nuclei.
Yeah.
What was the model? What was the input?
So the input. So the input was this. So we had this interaction at high order next to leading order in this chiral expansion. So leading order is one pion exchange and contact interactions. Then you go to two pion exchange and more complicated contact interactions. And so all the parameters were fitted essentially on the masses. So two nucleon parameters were fitted on the neutron proton phase shifts. And the other parameters were fitted on the three nucleon forces. So these are fits to these yellow ones. So then all the parameters are fixed. And then you can predict like the radii of these nuclei, and you can predict these.
So you put it on a three-dimensional lattice?
Yes.
How big is the lattice?
The lattice is, so the lattice spacing was 1.32 Fermi, and the physical length is about 12 to 16. So 12 times 1.3 times 16, 1.3. So something 15 to 20 Fermi. It's even in a nucleus like nickel-58, which is the size of 3.5 Fermi, finite volume effects are completely gone in a box of 15 Fermi. With periodic boundary conditions there. So you see that here, if you look at the matter at higher density, sometimes you have to work harder. Here you see this up and down. Then you have to put what is called twisted boundary conditions to get rid of these. These are effects from the finite volume, because you have so many nucleons. Twisted means you put some to the I theta on one instead of the periodic, and then you can tune the theta so that these effects go away. Comes from lattice QCD, which allows you to, the momentum is quantized on the lattice, it's pi over L, but if you have a twist angle, you get 2 pi over L plus theta, and then you can get a changing momentum. And this you can also use to get rid of such oscillations. So that's a technique which is well studied. We have shown this in some earlier paper on lattice thermodynamics where we showed that such effects really disappear. But here so this was done with periodic boundary conditions. We simply ran out of time because they are more computing time intensive. Oh, no. We choose it, no. So here the point is that, wrong direction, sorry. So here, what we tried first is to fit the nuclear forces only to light nuclei. But then you cannot describe the large nucleus. So you have to include one heavier nucleus like calcium-40. This is just, we tried many fits. And so you can never get if you say stop your fitting here, you will see that deviation starts here, sizable. So you have to include one higher nucleus. And then the other ones are put because there are certain structures which are known to be important, so you use them in the fit. But it's not so sensitive. The point is that you need some data points from the low side, you need some data points from the medium side, and one from the heavier side, at least. So for example, in the original paper, we had only up to calcium-40, but then the referees were not happy. So then we used the same parameters, and you see that chromium-50 and nickel-58 come out quite nicely. Oh, for example, instead of fitting to helium-3, we could also fit to hydrogen-3. That's a matter of taste, what you take.
How much?
Yeah. So this is a prediction, the radii. This is a prediction, the equation of state for neutron matter, nuclear matter, all the same, nothing fixed anymore. This is a prediction, the isotopic change of oxygen and carbon. This is a prediction. And then there are more. Not this one. Then there are more which we didn't even show. Like, for example, we have done alpha particle scattering on carbon-12, which is the first reaction for alpha carbon to oxygen-16 plus gamma. This comes out nicely in the SP and D waves and other things. We have just published a paper on the archive for neutron alpha scattering, which is sensitive to three-body forcing, comes out nicely. So we don't change parameters anymore. We fix them once, and everything else I've shown you are predictions. There are more, which I, for the sake of, I didn't want to overflood you with plots. But it's very predictive. So many things you can do. And in particular, nice is this beryllium stuff, because you have really very complicated, these are pictorials of course only, but you have very complicated structures like 2 alpha particles loosely bound, then extra neutrons, 1 or 2 in various orbits. So this one is around like this one is around about the middle, and all these come out correctly if you look at the spectra. And also then we calculated radii and electromagnetic transition. It's as they know, and they also agree with experimental data. It's just a big table which I don't want to show. And particularly important is this beryllium 11 ground state 1/2 plus, which in most calculations the 1/2 minus is a ground state, but experimentally is the 1/2 plus. The 1/2 minus is not far away, and we get this also as a ground state. So all this is output. So this is not fixed. This is not pushed. There's nothing changed here in the parameters.
I think we have run out of time, and so it's better to end here, and let's thank the speaker again.